Let's dive right into this explainer. Today, we are exploring an absolute modern miracle that pretty much all of us carry around in our pockets every single day. I'm talking about the invisible, microscopic magic that makes modern smartphone photography possible. We're going to trace the fascinating journey of camera sensors, looking closely at how engineers literally coaxed tiny, rigid pieces of silicon into capturing the world around us in such vivid detail. Have you ever actually stopped to think about it? How exactly do our smartphones capture these flawless photos in dimly lit restaurants or at a dark concert without needing some massive, bulky flash? How on earth did we go from giant, heavy cameras to a tiny little lens on the back of a phone that can essentially see in the dark? Well, to understand this, we need to look at the core mystery of how engineers taught silicon to process light and the absolutely incredible roadblocks they had to smash through to get us here. To set the stage, let's look at the initial engineering rivalry in the early digital imaging world. On one side, you had the charge-coupled device, or CCD. Now, CCDs produced beautiful, high-quality images, but they were incredibly power-hungry and required super specialized manufacturing. On the flip side, we had the early passive pixel sensor, or PPS. The PPS was a neat idea because it consumed very little power, but it had one massive flaw: high noise. You see, early passive pixels didn't have their own amplifiers, which meant by the time the signal was actually read, the image was already degraded. Okay, let's dive right into Section 1, Dawn of Digital Pixels, the first roadblocks, and see why the initial reigning champion of digital photography eventually had to be dethroned. So, the charge-coupled device was invented way back in 1969 by Willard Boyle and George E. Smith. And for a really long time, CCDs were the absolute gold standard for image quality. But there was a major catch. A CCD relies on a nearly perfect charge transfer during its readout phase. It's kind of like a bucket brigade, passing the electrical charge from one pixel to the next, bucket by bucket, all the way to the edge of the chip. This heavy reliance made them slow, notoriously power-hungry, and honestly really difficult to manufacture in large, high-resolution arrays. If you tried putting an early CCD into your modern smartphone today, it would overheat and completely drain your battery in no time flat. So, as the demand for portable, high-resolution digital cameras started to explode, the industry faced a massive wall. How do we solve the power and scale problems of the CCD while maintaining or, even improving the image quality? Well, the answer was actually found in a completely different sector of the tech industry. Moving on to Section 2, the CMOS revolution. Because instead of trying to reinvent the wheel, engineers realized they could just use well-established semiconductor manufacturing processes to fix the CCD's flaws. Here is how rapidly things changed. In 1969, the CCD is invented, but then a series of rapid breakthroughs totally shifted the landscape. In 1980, the pinned photodiode is created at NEC, which drastically lowered lag and noise. Fast forward a bit to 1985, a team at Olympus fabricated the first MOS active pixel sensor. And finally, in 1993, a team at NASA's Jet Propulsion Laboratory developed the very first CMOS active pixel sensor. They basically married the active pixel design with standard, highly efficient CMOS manufacturing. And just like that, the modern camera sensor was born. But what does that term active pixel sensor actually mean? Well, an active pixel sensor, or APS, is a sensor where each individual pixel unit contains its very own active transistor amplifier. Unlike the old passive pixel sensors that just sat there passively collecting light, putting an amplifier directly inside the pixel itself was the critical leap. It immediately reduced noise, it dramatically sped up readout times, and it allowed engineers to integrate image processing functions right onto the exact same chip. Now, to be fair, early CMOS technology wasn't completely perfect right out of the gate. Because a CMOS sensor typically captures a row of pixels at a time, refreshing from top to bottom, it created a temporary drawback known as the rolling shutter effect. If you've ever taken a photo of something moving fast, like a car driving past you, and noticed the car or the background appears weirdly skewed or kind of leaning to one side, yeah, that's the rolling shutter. Because the top of the frame is captured just slightly before the bottom, that fast motion causes the whole image to bend. Let's get into Section 3, inside the active pixel. We're going to zoom into the microscopic anatomy of a modern active pixel to see exactly how this incredible engineering works on a molecular level. Okay, let's walk through the standard 4T cell process, meaning a cell with 4 tiny transistors. Now keep in mind, all of this happens in a fraction of a second when you take a photo. Step 1 is the reset. A transistor connects the photodiode to the power supply, clearing out any lingering electrical charge, so you start with a totally clean slate. Next step is step 2, photodetection. This is where the pinned photodiode absorbs incoming light photons and converts them into an electrical charge. Step 3 is transfer. A gate opens, moving this entire charge to a holding area called the floating diffusion. And finally, step 4 is readout. The source-follower transistor acts as an amplifier, reading that voltage without actually removing the charge and sends the signal right down the line. And the crazy part? All of this happens millions of times across the sensor simultaneously. But as smartphone manufacturers started demanding thinner phones and way higher megapixel counts, engineers hit another physical limit. When you pack more pixels onto a tiny sensor, the pixels themselves naturally have to shrink. And guess what? Smaller pixels collect less light. So the ultimate engineering dilemma became, how on earth do we capture more light without making the pixels bigger? That brings us to section 4, the back-illuminated breakthrough. Now, what's really interesting here is the genius, almost completely counterintuitive solution the industry came up with by physically flipping the script. Think of a traditional front-illuminated sensor as being built a lot like a vertebrate eye, like a human eye. The matrix of wiring sits right on top of the light-sensitive photocathode layer. This means the incoming light has to navigate through this microscopic metal maze, and a lot of it just gets blocked or reflected away. But a back-illuminated or BSI sensor takes an astonishing cue from the cephalopod eye, like a squid's eye. Engineers took the silicon wafer, completely flipped it over, and thinned out the backside. So now, the light strikes the photocathode layer directly, with all that messy wiring tucked neatly behind it. The results of this biological mimicry were just staggering. Moving the wiring out of the way increased the chance of capturing an incoming photon from about 60% to over 90%. To put that into photography terms, that essentially made the camera a half stop faster. Suddenly, these tiny little sensors were capturing significantly more light, vastly improving performance in partial sun and dimly lit environments. A total game changer. Now, thinning these silicon wafers out initially made them incredibly fragile, which caused some pretty low manufacturing yields early on. But by 2009, Sony reduced these problems enough to launch the Exmor-R, bringing a 5-megapixel back-illuminated sensor to general consumer prices. And just a year later, Apple adopted an Omnivision BSI sensor for the iPhone 4, which garnered absolutely massive praise for its stunning low-light photos. This one piece of technology single-handedly revolutionized smartphone photography and honestly fueled the massive rise of social media sharing as we know it today. But you know how it goes, innovation doesn't sleep. As sensors got faster, they needed more onboard processing power, which meant more complex circuitry. But if the pixel area is completely dedicated to capturing light, what happens when we run out of horizontal space on the chip for all that processing power? Welcome to Section 5, Stacked Sensors and Beyond. Because when you hit the physical limits of horizontal scaling, you have to start thinking vertically. The answer is simple. If you can't build out, you build down. A stacked CMOS sensor takes that back-illuminated concept we just talked about and supercharges it. Instead of just putting the wiring behind the light-gathering pixels, engineers actually managed to layer the complex processing circuitry and image signal processors directly beneath the pixel section itself. Announced by Sony in 2012, this vertical stacking meant the active pixel could occupy even more surface area, resulting in another 30% increase in captured light. This architectural marvel just unlocked some unbelievable capabilities. Because the processing chips were stacked right underneath, data could move vertically at blazing fast speeds. We're talking vastly faster frame rates, advanced on-chip processing, and finally eradicating that pesky rolling shutter distortion we mentioned earlier. And while this tech started in smartphones and action cameras like the GoPro, it definitely didn't stay there. Today, stacked, back-illuminated CMOS sensors are the driving force behind the absolute highest-end, professional, full-frame, and medium-format cameras on the market. So where do we possibly go from here? Well, researchers are already looking at a massive potential paradigm shift called the quanta image sensor, or QIS. The concept here is just breathtaking. Rather than capturing standard pixels, the goal of QIS is to count every single individual photon of light that strikes the sensor. Using a billion or more specialized photo elements, called JOTs, this sensor would read out bit planes hundreds or thousands of times per second. That would generate an absolutely mind-boggling terabits of data per second. While the quanta image sensor is still largely experimental just due to its sheer complexity, it leaves us with a really incredible realization. From clunky, power-hungry CCDs to microscopic layers of thinned silicon mimicking a squid's eye, engineers have continually bent the laws of physics to fit inside our pockets. It really begs the question, If we can eventually count individual photons, what are the actual physical limits of capturing light? Next time you snap a photo in a dimly lit room, just remember the invisible microscopic magic making it happen. Thanks for exploring with me on this explainer, and keep asking questions.